So I'll first begin with the multiphase flow part of the talk. And this was part of my postdoc work that I did at Cornell. So thanks to my colleagues, Robert and Michael Kuhn, and my advisor, Olivier Desjardins. So in this part, the numerical methods that you're going to see is not developed by me. It was already existing in their single mesh code framework called NGA. So my work was to interface that code framework into the data structures of AMReX. So coming to the governing equations, the algorithm used an unsplit geometric WOF, volume of fluid. So geometric means that wherever there is a liquid-gas interface, we create a single plane, very similar to what we have in EB in AMReX, and that is advected passively with the velocity field. So that is, you have one equation for the volume of fluid transport, which is the first one, and then you have 5 equations for the gas and 5 equations for the liquid. So totally 11 equations are being solved, and we have a stiffened gas equation of state to account for the multiphase nature. And the interface reconstruction, I'm not going to the details, but it's done through something called as PLIC, which stands for piecewise linear interface calculation. So there is a way of determining the normal to the plane by a least squares error reduction method, and that's how you determine the interface. And we have an all-Mach algorithm, which means that it is going to work on all ranges of Mach number, and it is in the same spirit as any incompressible flow algorithm, in the way that when you do the advection, you do not have the pressure term, and then you bring back the pressure term with a projection step. And as opposed to an incompressible flow where you have a Poisson equation, you would have a Helmholtz equation for pressure in this case, because the pressure also has a time derivative term, unlike incompressible flows where that is missing. And in this, if you actually divide by the speed of sound, which is denoted by c, and if you make it go to infinity, which is the incompressible limit, you will recover the standard Poisson equation for pressure in the incompressible limit. And then you have a correction step very similar to what you have in incompressible flows. So one of the key aspects in the state-of-the-art primary atomization multiphase flows that they had in their solver is this idea of semi-Lagrangian advection that leads to a discretely conservative solver. So the way it works is that if you want to advance the variables in a given cell, you trace back the cell by delta t, and you join the phases and you form the geometry. And here I'm showing only a very simple convex geometry, but you can imagine how it can have all sorts of shapes, concave and overlap on each other, like to form like an X kind of shape and so on. So, and once you form this, and you can show by a rigorous control volume analysis that the content in the red box at Tn is the same as the content in the blue box at Tn plus 1. So it's the idea of Lagrangian, like a particle moving from A to B. It's what fluid patch is moving from A to B. That's the idea. And now it has reduced, it does not reduce, it's become a geometric problem. Now you have to find the volume of this red box. And to do that, they have a simplex tessellation method where they divide the volume into tetrahedra. So first, the volume is cut by the mesh, the mesh faces, and wherever you encounter a non-tetrahedral volume, you further divide it into tetrahedra. And this process handles all sorts of geometries like concave and all overlapping stuff and so on. And then once you form the tetrahedra, you have a gradient reconstruction algorithm to compute the variables at the centroids of the tetrahedra from the centroids of the cells where you have the actual data. And from that, you reconstruct the solution, and then you add up all of those to get your final update. And once if you have a interface there, which means you have liquid and gas, then you will have further regions which are non-tetrahedral, and then you divide them into tetrahedral. And by this process, the advantage that they get is that they can advect the gas and the liquid separately, and that's how it is discretely conservative. And it is unsplit, like what we do in a finite volume scheme by finding fluxes on each of the phases. We do not directionally split things in the x, y, or z direction. And as part of his PhD work, my colleague at Cornell, Rob Chiodi, he had packed all these things that I described nicely into a library called the Interface Reconstruction Library. It's written in C++, but it also has Fortran interfaces. And I was using the Fortran interface of AMReX at that time. So yeah, this was incorporated within the AMReX framework to do all of those. So all the numerical methods were handled by them. So I only handled interfacing them, porting those routines one by one into the AMReX data structures. And we did a bunch of cases, some verification cases, and then moved on to doing some real, quote unquote, real problems. So this was one project from the funded by the Air Force Research Laboratory. They were looking at fuel atomization in a liquid jet and supersonic crossflow configuration. So here what you're seeing is there is a Mach 1.94 crossflow of air going from left to right. And there is a fuel jet at 20 meters per second. It's a water jet, so the density ratio is 1:1000. And it's 1 millimeter diameter. And there are 3 levels of refinement above the base level. So that gives about 18 points in the jet diameter. I do not have any quantitative comparisons or anything. These are more like qualitative. And yeah, it's just to see that the simulation runs in a stable manner. So as you can see, this the refinement was based on the interfaces. So wherever there is an interface, I tag them for refinement. And the boxes show the finest level of refinement. It's also customary to render these simulations in Blender. So here what you are seeing are the actual interface planes. So those planes are exported as STL formats from Visit, which can be read in Blender and which can be visualized. There's not much scientific value. It's just a nice simulation. So, and the other thing, other project that we had was funded by the Office of Naval Research, in which they were looking at atomization using acoustic waves. So they had transverse acoustic waves that create a standing wave pattern when they come from both the left and the right, and they atomize the liquid. And based on where the liquid jet is located on the wave, so here on the top you can see the experiments, and the PAN is pressure antinode, IAN is intensity antinode, and VAN stands for velocity antinode. So based on where the location is, you will get different atomization patterns. When the liquid jet is aligned with the PAN, then you don't have, although it is a maximum pressure, you do not have any gradient there, and so it might lead to thinning of the jet, but it does not lead to atomization. So you always need some sort of an asymmetry, like what you have at IAN or the velocity antinode, and it's not really apparent. So one of the velocity antinode is having a more symmetric pattern, whereas the intensity antinode has a sort of a bias in atomization towards one side. And this is another view of the simulation. Again, all qualitative comparisons with the experiment on the left and the simulation rendered in Blender on the right. And this shows a view of the finest level of refinement, which is there were 3 levels of refinement above the base level. And also did some studies of scalability of bubble collapse in supersonic flow on the Stampede, now obsolete night landing nodes. And it was a decent scaling with AMR, and the resource usage was reduced by about 50% with adaptive mesh refinement of 3 levels with a 64 cube mesh. And the next part is the work I did at NREL, thanks to my co-authors, Ray, Weichen, and Mark. And this is on implementation of a moving embedded boundary algorithm within the CNS framework, which is the Compressible Navier-Stokes framework in AMReX. So CNS framework has an existing capability of doing simulations with compressible flow and static bodies. So that was extended to doing moving geometries. And it has a Godunov-based semi-analytic Riemann solver with band-layer limiting of the fluxes. It has a second-order accuracy, and the small cell issue was treated with the flux redistribution technique. And because this is an explicit solver, it does not have the issues that Deepak was mentioning in the morning related to solver convergence, like the nodal Poisson convergence or anything of that sort. So here, I'm not going to the details of how the fluxes were formed, but the idea is that at every phase, even at the EB phase, you have a left state and a right state, and that's given to a Riemann solver, and that returns you the fluxes at the EB phase. So to do a moving EB, the fluxes, the state within the inside the EB was modified in a certain way so as to account for the moving boundary condition. And one main thing that has to be handled is what are called as freshly cleared cells, which means that when an EB is moving, you have cells which were previously solid and suddenly they become a cut cell or like a fluid cell, and which does not have any history of fluid data. So you have to do some sort of an interpolation. So we do interpolation from the valid cells, which are like the cut cells or the fluid cells, in a 3x3 neighborhood, and it is a volume weighted average that is being done. And we did a bunch of test cases. These are some inviscid test cases. So there's interaction of a wedge with a shock. There are 4 levels of refinement above the base level, so total of 5-level mesh. And there are some qualitative comparisons with the experiments showing that it has a lot of the features that are like accelerated shock, decelerated shock, expansion fan, and so on. And another comparison with experiments in a quantitative sense is that what is known as a transonic buffet, and it consists of subsonic flow which accelerates on top of an oscillating airfoil about the quarter chord point, and on the right is a comparison showing the coefficient of pressure at the bottom and top of the airfoil, and also a comparison of how the lift coefficient changes as the airfoil oscillates, and the 3-dimensional qualitative comparisons with test cases that have been done in literature of a cone interacting with the shock, and this shows the boxes at the finest level of refinement. There were 3 levels above the base level in here as well. And another thing that we had done was to implement a better method for computing the viscous gradients on the surface of the EB. So the classic method consists of a 3-point method to find the gradients along a line normal to the EB, and we replaced that with a 3rd-order least squares method, which is also now there in AMReX Hydro. And so to do this, I had an implementation of that within the CNS solver, which used LAPACK to solve the 9x9 matrix system, and it's a pointwise matrix system, and it is so that's pretty fast. And we did a bunch of test cases to verify that. So this is one of the cases where there is a oscillating cylinder with a frequency of oscillation same as the vortex shedding frequency, and we have some comparisons of the coefficient of pressure with some experimental data which is shown in symbols, and also the skin friction coefficient at this shows at 2 different frequencies of oscillation. And I'll stop my simulation with AMReX logo represented as a moving embedded geometry with 4 levels of refinement, 3 levels of refinement above the base level. So yeah, that's yeah. I'll take questions.
The multiphase stuff at the beginning, you included her big decision?
their code had, but no, I have not included the substantial. Yeah, that was some extra things that I had to do. For, yes, yeah, that was not that. But the things that I was trying was high Weber number or low Weber number or whatever. The surface tension is not really important in the breakup that you are seeing in those cases. Right? High Weber number. Okay, I forgot if it is in the denominator. Yeah, that's right. Yes. Yeah.
For Multiphase stuff, so from the results, we see that the jet breaks up in small particles. But what happens when the particle size becomes smaller than the grain itself? Like, does it conserve mass? Is it dissipate?
Uh, yes. So in the simulation that I showed, there was only one plane in each cell where there's an interface. Rob, who was the developer of the library that I took, he had developed a method where you can have multiple planes within a given cell. So that will give you subcell resolution. Okay. So that was the resolution that they found, that we need to have 2 planes or even 3 planes in a cell to have that sort of resolution.
So the mass is always conserved.
It is. But in these simulations, it is, if you want to resolve that droplet, you need to have more finer mesh because there are no multiple planes. So if you could capture like very thin sheets and so on, and get some very interesting things.
You wish I knew all about it.
Oh, yeah.
I have one more question actually. That's good if you always the EV stuff, so there's an issue of freshly clear cells where you have new cell open up, when you interpolate. But there's also an issue of when the cell goes from fluid to solid. So what happens to the mass of the
I do not do anything good. So this was I presented to say that Sam and Master about the Sir and George, we were talking about that. They said we probably should account for that as well. I do not do closing of a cell. It's like you have to push that mass into the negative. I do not do anything good, but reasonable quantitative comparisons with all three things. Have you found anything different?
Yeah, it matters when we have kind of supersonic like attenuation like such things. Because the mass resolution because the right shot is
Maybe I've not encountered those things. These are probably much more simpler compared to that. Yeah. No. So all of these, the answer is no. So all of these were within the AMReX framework at the time when it was C++ and program. So these are not C3 as well. The only thing I think it's a problematic thing is that you need to have ghost cells, enough ghost cells to account for, because you are backtracing a particular cell, you cannot go past the number of ghost cells that you have. It has to be. So that is the only thing that they are actually you need to have that. But for that, I think should be just what's in your mind like is there anything that you find particularly challenging in GPU?
Oh, I haven't tried this, but just making.
No problem.
All right, let's thank our speaker.